Okay, let's talk about average rate of change problems. We're going to solve some practical problems today. First of all, let's look at some keywords you might notice as you go through this lesson. First of all, average speed. Okay, so driving from one place to another. Not your instantaneous speed, but what your average speed might be over time. Next, we have change in temperature as elevation increases. We're going to see that in an example. When you climb up, your temperature is going to go down. When you climb down, typically the temperature goes up due to elevation. Next, we have change in weight over time. If you see something like that, did not mean to go to the next example. If you see change in weight over time, that is likely a average rate of change problem. And finally, change in f of x over change in x. So when you have a period of time that spans, okay, whenever time changes, that's typically average rate of change. Instantaneous rate of change is at a particular point in time, which we'll talk about in another lesson. So let's go ahead and read this first example together. A rock is dropped from a cliff at time t equals 0. Its vertical position is in feet from the cliff, and it is given by the following equation, which is the equation for gravity, negative 4.9 t squared. So basically, if you were to plug in 0 here, the position would be 0, right? It would haven't fallen on any from the cliff. If you plug in 1, you get negative 4.9 feet, which would mean it's fallen 4.9 feet after 1 second. So that's what this equation means. Now let's get to the actual question. What is the rock's average velocity between 2 and 2.5 seconds? So what this question is actually asking is, between 2.5 seconds, what's its average speed? Now velocity just means direction, so it's going down. So we're not asking about instantaneous rate of change, but what's its average velocity during that time. I always recommend drawing a picture for your first step, especially for any word problem. Here's our top of the cliff. Here's the rock that we dropped. Remember, we dropped it from the top, and didn't mean to do that. So anyway, you can tell that after t equals 2 seconds, it's going to have dropped a certain distance already, right? And then it's going to fall more until t equals 2.5. So the real question is, how fast is it going on average between t equals 2 and t equals 2.5? This is what we're going to figure out. All right, step 2 is to convert words to variables, okay? So the average velocity we will write as change in s over change in t, all right? Between 2 and 2.5, we will make t1 2 and t2 2.5, and its vertical position we will call s of t. Pretty simple. Now, why does S mean position? I'm not sure. Okay, we use S for position, V for velocity, A for acceleration. So I'm not exactly sure about that, but S means position, particularly S of t. Step 3, write out the known values. So now that we've determined what our variables are, T1 is going to be 2, T2, our time 2 is 2.5. Our position equation is what was given to us, negative 4.9 t squared. T not equals 0 is irrelevant because we're not using it to solve this problem. However, just write it everything you know just in case. All right, so then the next step is just to write out your equation. Average velocity, change in s over change in t. Now it's not s prime of t, as we'll learn is instantaneous. It's change in s over change in t. S of t2 minus s of t1 over t2 minus t1. Same thing as y2 minus y1 over x2 minus x1. So this, in fact, is the slope of the secant line, as we've learned before. Now we're going to plug in our known values. We know that time 2 is 2.5 and time 1 is 2. However, in order to solve for our average rate of change, we need to know these other two variables, right? So basically 5 variables in this equation. This is 1 and then 2 on top, 2 on bottom. Leads us to our next step. In order to solve for that variable, we have to figure out these two things on the top. So step 6 is to determine the additional unknown. We can do that though because we were given an equation for position. So we can just plug in our value for t1 and figure out what s of t1 is and do the same thing for t2. All right, so when we plug in t1, 2, we do some math and we get negative 19.6, which means that that rock has fallen 19.6 meters after 2 seconds. So this right here, this distance would be 19.2. All right, and then if we plug in our t2 value, we get negative 30.625, which means after t equals 2.5, it would have fallen about 30 feet. Okay, so we need to know that in order to figure out the average rate of change. Let's go ahead and do that now. Now that we figure out those other unknown values, we can plug them to this equation. You can use your calculator, however you want to solve this. You end up with an average rate of change of 22.05 negative, which means it's falling at a rate of 22.05 feet per second on average. That is its average velocity. Okay, so going back to the picture for the sake of comprehension, now in between here and here, on average, it's falling around 22 point whatever feet per second. Now, it doesn't mean that it's always falling that. That's its average. Of course, it's going to be falling slower here than it is here due to gravity. We'll learn later that because that's its average rate of change, at some point its instantaneous rate of change must also be 22.05. But for now, that's its average velocity. If you have any other questions about this example or average rate of change problems, let me know.